Hello, I'm Mr. Bob, and welcome to my Geometry Review video series. This video covers Chapter 9, Section 2, titled Sine and Cosine Ratios. By the end of this video, you will have reviewed recent lessons describing sine and cosine ratios. Discussions will include using sine and cosine in triangles, writing sine and cosine ratios, and using the inverse of sine and cosine. We'll also look at a real-world problem that requires the use of sine ratio for its solution. If you'd like me to cover any of these topics in greater detail, please leave a request in the comment section below. Please subscribe to this channel if you find the videos to be helpful. Thank you. Okay, so before we get started, we'll look at a definition here, a couple definitions. One, sine. The sine of angle A is equal to the leg opposite angle A divided by the hypotenuse. So that's, if this is, we're looking at angle A right here, here's angle A. The side opposite is this one over here from B to C, B to C, and it's divided by, that length divided by the hypotenuse, and the hypotenuse is defined as the side that's opposite the 90 degree angle. So C in this case, as we see here, is 90 degrees. The hypotenuse is the side that's opposite that. So we're looking at the sine of angle A is the leg opposite, A divided by the hypotenuse. So it's BC divided by BA. The cosine of angle A is the leg adjacent to angle A. So now that one's AC, I'll change colors here, AC divided by the hypotenuse. The length of AC divided by the length of AB. That's the cosine. So the way, and then for identity purposes, the way to describe the relationship between sine and cosine is to say that the sine of x degrees is equal to the cosine of the quantity 90 minus x degrees. So if the sine of x in x is 30, the cosine of that, to get that same result, would be 60, right? 60 degrees. 90 minus 30 would be 60 degrees. Okay. Okay, objective 1, using sine and cosine in triangles. We're going to repeat the same thing we just saw in the definitions, because this is where the definition came from. So a tangent ratio, as you had seen, involves both legs of a right triangle. The sine and cosine ratios involve one leg and the hypotenuse. So when we're doing tangent, we're like using the leg opposite divided by the leg adjacent. Adjacent, opposite, right? Opposite divided by adjacent. But for sine, it's the opposite divided by the hypotenuse, as we just stated before, and the cosine is the adjacent divided by the hypotenuse. Okay? And these equations can be abbreviated as sine A is equal to opposite over hypotenuse, and cosine A is adjacent divided by hypotenuse. So example 1, writing sine and cosine ratios. It says use the triangle to write each ratio. And they've listed 4 of them here, A, B, C, and D. Starting with A, we have, what's the sine T? Sine of angle T. Well, angle T is right here. This is angle T. And what do we know about the sine of T? The opposite side divided by the hypotenuse. So the sine of T, the opposite is here is the side with the length 8, and the hypotenuse is 17. So if we take the opposite divided by the hypotenuse, or 8 divided by 17, that is the sine of angle T. And we can do the same thing for cosine. Cosine is the side adjacent divided by the hypotenuse. Well, here's again angle T. Adjacent, as we know, is the leg that is touching the angle, and the hypotenuse is the side that's opposite the 90 degree angle. So 15 divided by 17, and here we are, 15 divided by 17. How about the sine of angle G? Well, now we're going to switch up here to G. I'll switch to red. How's that? So now we're going to be up here at angle G, and we want to know what is the sine of angle G. Well, the sine is opposite. So the side opposite, right here, angle G, divided by the hypotenuse. 15 divided by 17. Here it is right here, 15. Well, but you notice here that the sine of g is the cosine of t, is the same number. Okay, interesting. So the cosine of g is the side adjacent, which is the 8. 8 is adjacent, and the 17, again, is the hypotenuse. So it's 8 divided by 17. So those are the 4 types of trigonometric functions that we can come up with on these 2 angles. Okay, example 1, check your understanding. They'd like you to write sine and cosine ratios for angle x and y using the diagram below. And then generally want to know how are the sine of x and the cosine of y related, and then kind of explain. Okay, so go ahead and take some time, stop the video. When you come back, we'll continue on. Okay, I'm assuming you stopped it, you've tried it, so let's give them a shot. Let's see what we have here. So if we look at angle x, here's angle x right here, angle x. We want to know what is the sine of angle x. They give us all the numbers we need here. Well, we know the sine is the side opposite divided by the hypotenuse. Well, so we're going to get the sine of angle x is equal to what? It's equal to the opposite, 64, divided by 80, the hypotenuse. So it's equal to 64 divided by 80. How about the cosine? Cosine of x is equal to, here's x, cosine is the side adjacent divided by the hypotenuse. So it's 48 divided by, oops, that's an 8, 80. And now we have the sine of y. The sine of y is equal to, here's y, the side opposite is 48 divided by the hypotenuse. 48 divided by the hypotenuse, again, is 80. And then we have the cosine of y. And that's equal to, cosine is the side adjacent, 64 divided by 80 is 64 divided by 80. Okay, so then it says, in general, how are sine and cosine, the sine of x and cosine of y related? Well, they're complementary. Okay, so both of them, when you're done, the ratios sum up and equal 90 degrees. So that's basically what we have here. Okay, example 2, a real-world problem. The trigonometric ratios have been known for centuries by peoples in many cultures. The Polish astronomer Nicholas Copernicus, from 1473 to 1543, developed a method for determining the size of orbits of planets closer to the Sun than the Earth. The key to his method was determining when the planets were in the position shown in the diagram here to the right, and then measure the angle A. Okay, so if A is equal to 22.3 degrees for Mercury, how far is Mercury from the Sun in astronomical units, or AUs they call them? One astronomical unit is defined as the average distance from the Earth to the center of the Sun, which is about 93 million miles. So what did they do? You take a look. So we have the angle of A we're trying to determine, and we all want to, well, we determine that by measuring, and then we want to find out the distance of the planet. Mercury, in this case, is from the center of the Sun, and that distance is x. And the 1 AU, the one astronomical unit, is from the center of the Sun to the center of the Earth. And we determined that was 93 million miles. So what are we going to do? We're going to take the sine of 23, the sine of 22, right here. The sine of 22.3 is equal to x divided by 1. Since we're doing 1 is the astronomical units, we can see that the sine is the opposite. Here's angle A right here. Angle A, and the opposite is x, is the side opposite A. And the astronomical unit that they're showing right here, this 1 AU, is the hypotenuse of this right triangle that we're determining here by looking at this tangent line to the center of Mercury from the center of the Sun. So if to solve it, then it's x divided by 1, because we're measuring in AUs. So if you take the sine of 22.3 degrees is equal to x divided by 1, we can say x is equal to the sine of 22.3 degrees. Okay, so in doing that, we're going to solve with that by just running it through the calculator. And we'll find out that when we do that, x is equal to 0.379455616 astronomical units. So Mercury is about 0.38 AUs from the sun. Okay, example 2, check your understanding. So they want us to solve the same problem we just did in the previous slide. And we're saying that if A, the angle that we've talked about here before, from the center of the sun to the center of, now in this case, Venus, at when it's at a point that is the tangent to the diameter of the, or to the orbit of Venus, is 46 degrees. How far is Venus from the sun in astronomical units? And then also they ask, how many miles from the sun is Venus and Mercury? So they want you to do that calculation also. So why don't you go ahead and do that, and then when you're done, restart the video, and we'll continue on from there. Okay, I've given you some time to do that. I'm sure you've got the answers. So let's take a look at it. Same as we did before. If A is equal to 46 degrees for Venus, how far is Venus from the sun in astronomical units? So the sine, as what we did before, we're trying to find x, which is this guy right over here, this x right here. We're trying to find that distance from the center of the sun to the center of Venus now, which is x. So we say the sine of 46 degrees, and x is the side opposite, and the tangent is, the hypotenuse is the distance from the sun to the earth, 1 astronomical unit. We get the sine of 46 degrees equals x divided by 1, which is just x. So we can say the sine of 46 degrees equals to x. And what is the sine of 46 degrees? Well, the sine of 46 degrees is equal to 0.719339. And that's it. So x is equal to 0.72 AUs. So that's the answer there. And so how many miles is the sun from Venus and from Mercury? Well, I did Mercury first. So that was from the previous slide. We know that it was 0.38 AUs. So, and the distance for that 1 AU is 93 million miles. So 0.38 times 93 million is 35.340, not 35.340,000 miles. Okay. And then for Venus, it's 0.72. So we have 93 times 0.72 is equal to 66,960. Okay, so 66,960,000 miles. Okay, good job. Okay, example 3, using the inverse of cosine and sine. So what we're going to do now is we're going to use the lengths to determine what the angle is. In the past, we knew what the leg lengths and the angle was to find another leg, but this time we want to find the angle. And we do that by using the inverse cosine or the inverse sine. These methods are on your calculator. If you look at your calculator, if you look at the sine button above it, it'll say sine inverse, sine to the -1. And usually that's like a second function, like you'll touch, or a shift function. You say shift sine or shift or second or whatever the button is for doing the functions above the button. And sine, cosine, and tangent, all three of those have an inverse. So in our case here, it says, so when you know the leg and hypotenuse of a right triangle, you can use the inverse of sine and the inverse of cosine to find the measure of the acute angle. Okay, to find the measure of angle L in our diagram here, Well, it says find measure of angle L to the nearest degree. Well, first of all, we have to figure out what is the angle L, and then we need to know what is the side opposite and or adjacent, whichever one we want to use. We can use probably either of these, but does it say to use a cosine or sine? It doesn't. It doesn't say which one we have to use per se here in the problem. But we're going to do two different methods here. We're going to show. In fact, we're going to just do them both ways. Okay. So first of all, look at for angle L. Let's do the cosine of angle L. So here's angle L right up here in the top of the triangle. Here's angle L right there. And we're going to do the cosine. Method 1 says the cosine of L is equal to 2.5. Here's the 2.5. So it's the side adjacent divided by the hypotenuse. And the hypotenuse is right here, 40 or 4.0. So 2.5 divided by 4.0 is 5.8. Okay, so if we follow through on that, now we put the measure of angle L. What is that angle L? Well, we can find that out by taking the inverse cosine, cos minus 1, cos to the minus 1 right there. You see the minus 1 right there, of 5/8. So you type in shift or second or whatever it says for your function button, shift cosine, and then enter in 5 divided by 8, and you're going to end up with a number 51.317813. Well, that is the angle. So if you take that and they say to the nearest degree, so that rounded is to 51 degrees. So the angle measure, or angle L, is 51 degrees. Now we can do the same thing with method 2. This case, we're going to use the sine. That's the other method. So find the trigonometric ratio. Sine of angle L is equal to 31. Here's the 31. Angle L is here. The side opposite is 31. And that's divided by 40. 31 divided by 4. So the inverse trig function, the sine inverse, like we said, second, sine inverse, you hit the sine button to get the sine inverse. And then you type in 3.1 divided by 4.0. And when you do that, your calculator is going to come up with 50.805033. And if we round that, we're going to get the measure of angle L using the sine inverse is 51 degrees, approximately 51 degrees. And by the way, once we take this calculator function, the answers are all approximate. Unless the number comes out exactly 2.671 and it ends right there. Other than that, if it's just a continuous string of numbers, it's an approximate answer. Okay? So that's it. Okay, example 3. Check your understanding. So this time you're going to stop the video and try to solve these yourselves, and then we'll do them together. But what are the problems? Is find the value of x. Round your answer to the nearest degree. And you have two different problems, problem A and problem B. So take a look at them and see if you can solve them, and then come on back. I'll give you some time. Okay, now that you've had some time to look at it, let's and work them out for yourselves. Let's give it a try. So problem A shows a triangle. They're looking for x in degrees. And first of all, to solve this, you need to find out, well, what am I looking at? I'm giving the side opposite, x, and the hypotenuse. So side opposite should imply right away that it's going to be a sine. Okay, so knowing that, we're going to say that x is equal to the inverse sine to the minus 1 of 6.5 divided by 10. And when you do that, when you run that in your calculator, as we talked about before, hit the second function or whatever it's called, shift or whatever, and then go to your sine button, and it'll show it above the button. So it's going to be the sine inverse, 6.5 divided by 10, will give you x approximately equal to 40.541601. That's in degrees, and it's going to be approximate because that value there, 6.5 divided by 10, is not an integer by any means. Or, you know what I'm saying? It's not going to end. It's not going to terminate. It's going to be a real number that goes on forever. So given that, the answer then, in rounding it to the nearest degree, is you have a 0.5, so that 0.5 will round up to 41. So x in degrees is approximately equal to 41 degrees. Now we look at problem B, and we have the same thing to decide. Is it sine or cosine, or are we looking for a tangent? What are we looking for? Well, we're given angle x, and we see the adjacent 10 here. This side right here is adjacent to the angle x, okay? So given that, and the hypotenuse, the side opposite the right angle, here is 27. So we're going to say x equals the cos inverse, the cosine inverse of 10, the adjacent side, divided by the hypotenuse. The cos inverse of 10 divided by 27 will give you the approximate value of 68.261539, on and on and on and on. Okay, and when that's in degrees. So we now have our angle in degrees. And so that angle is approximately, rounded to the nearest degree, the 0.2 will round down. So it's 68 degrees. Okay?